Welcome back, everyone, to Question Field, the place where you ask the questions and we field them. I am Brian Hannon.
And I'm Campbell McLaughlin.
And Campbell, I learned a few lessons that first batch of episodes. Number one, have my water ready to go. Or you could say I've already had most of it. And have a notepad in front of me. I'm ready to take notes tonight.
Fantastic. I have my trusty pen again, and a coffee for good luck.
When we get super famous and we have our first live show at Madison Square Garden, and you bring out the pen, the roar is going to be massive, massive.
It's going to have its own Twitter following soon.
Yeah. No, but we're here today to talk about something that's a little closer to my wheelhouse than, extra dimensions, potentially. And wheelhouse is actually maybe the perfect word for it, because we're talking about rotations. And I don't know, something about circular motion and spinning were like the thing that really made physics come alive for me in high school. And
cool.
Like I remember learning about it was the lesson on torque, and I was like, "Oh, you can do stuff with this. You can I felt like a Roman architect that day."
Yeah, I can finally understand what car freaks are talking about.
Yes, exactly. Yeah. But the other reason this is kind of near and dear to me is because I want to introduce this discussion on rotation with something a little bit musical. I mean, I'm a musical person. I mean, the people that are listening can't see, but anybody that's watching can see the wall of guitars and basses, right over my shoulder. I have a pretty big vinyl collection that I inherited, and obviously been into CDs since forever. But for a long time, I don't know if I understood how vinyl records worked. And I think I do. I guess we'll see if I finally have it figured out, right?
It's pretty complicated.
Yeah. It's kind of one of those things that it would be simpler to understand. And then I thought about it a little bit and I was like, wait a minute. And so here's the crux of where I used to be deep in the woods. You have a record, right? A vinyl record, and you play it, right? And obviously you have your needle, and the needle, as the songs are playing, right, the needle gets closer and closer towards the center. And as we know, right, the closer you are on your record, right, the slower it needs to go, right? And it's on the outsides, right? It's on the further out you go, right? That tangential velocity is going a lot quicker. And like that I understood.
Relative to the disc.
Yeah. So that's all good. That I had no issues with. But as a music person, and I think about songs, and songs always have so many beats per minute usually, right? And where I was getting, where the wires were getting crossed in my head was when it would, if the record is getting slower, right? The needle isn't going through the grooves as fast.
Yeah.
How is it that the song isn't changing its speed as well?
Right.
And let me test this explanation out on you, and let's see if I got it.
Okay, cool.
All right. So when they're cutting the vinyl, right, they have the master recording, and they're doing whatever it is they do, which I don't know. They're doing what they do to etch out the vinyl.
Yeah.
They must be cutting it. So a record player will spin at either 33 1/3 revolutions per minute, or 45 if it's a single or whatever.
Yeah.
I'm assuming they have to cut it at the same RPM. And the result of that, though, is that the reason the song doesn't speed up or slow down as it's going, as the needle is going through the etch, is because there's like different amounts of information content per length. And I guess it's, what would it be? It would be, you wouldn't need as much on the outside, but you would need more on the inside. Or maybe I have that backwards.
Yeah, so I guess the density is greater on the inside than it is on the outside.
Yeah, because if it's spinning faster, the closer, you would not need as much. And so that's, I know.
Yeah, it's getting,
so that's where I was going to end it, is I think the amount of like sonic content is in flux the whole time. But if you're cutting it at that flux, it all cancels out. So am I anywhere near close?
Well, I think that's the right idea, right? You've got the needle which is tracking the record, and it's going faster on the outside than it is on the inside, but it's recorded the same way as it's played. So when it's recorded, it's just the master is just rotating at a constant RPM, and when it's played, it's rotating at the same constant RPM.
Right.
And so it doesn't matter that the sort of information density or the music density is sort of greater on the inside than it is on the outside,
Right.
because you've already accounted for that when you recorded.
Okay.
So to be a bit more precise about it, most records are a diameter of 12 inches, I think.
Mm-hmm.
Or, I guess that's a standard size. So if you were, for example, if you were wanting to just have a really simple record with 1 click per second, right, and you've got a 12-inch diameter. Mm-hmm. So if you start with the needle at the very end, so it's traversing a circle with a diameter of 12 inches. So that means it's traversing a circumference of 12 times pi inches, right? So, and it needs to do that 33 and a third times per minute. So that's 33 and a third times 12 pi inches per minute. That makes sense?
Yes. Well, I mean, not that I can calculate 12 times pi times 33 and a third in my head, but yes,
I would not expect that in for you to do that on a pen and paper.
I can visualize it in my head. Yeah.
And I think that's about 21 inches per second. So you need to be putting, if you want, say, for example, that like 1 click per second, you need to be placing a little dot, something that will produce that click every 21 inches. And then when it's the closest to the pivot or to the center of the rotation, and you still want that 1 click per second, well, say the closest radius is going to be 1 inch. So when the record finishes, the needle will be 1 inch away from the center. Then you need 2 pi. There's 2 pi inches per revolution, and you're still having 33 and a third revolutions per minute. So we had 12 pi initially as the circumference, and now we have 2 pi. So it's going to be traveling. The needle is going to be traveling a sixth as fast as it previously was, right? So it's about 3.5 inches per second, because it was initially 21 inches per second. So those are a lot of numbers, perhaps, but so just to hammer it home, maybe, initially, if you wanted 1 click per second, you needed a dot every 21 inches.
Right.
And then at the end of the record, you need a dot every 3.5 or 3.5 inches. So it's just to show how that sort of information density increases.
Right.
So
I think we have our first bit of merch. We're going to sell vinyl. It's just a click.
Just a click track.
At every click, we'll have the dot on. They can make maybe they can make vinyls like that now, where they can get that precise. Yeah, and I guess what's kind of interesting then is, to that point, is like I had never really thought about it, but that would have to mean that the quality is also not the same. Like, if you have so much groove, right? I guess that means you would have higher quality. So the outside would be greater in quality?
I understand that to be the case. So I had to do a bit of research to find out about how records work and CDs work and things like that, and hopefully we can talk about that later. But yeah, my understanding is that the inner tracks are not as high quality, and so an audio engineer will apparently want to place maybe the less important songs and certainly the quieter songs at the inside. And the volume is kind of an interesting one. So maybe we'll get into that a bit later, but you actually need sort of more space for your song to be louder when you're inputting into a vinyl.
Interesting.
Talking about this like information density or sonic density with these records. Firstly, this is all because we're traveling. The record is traveling at a constant angular velocity, right? It's traveling at 33 and a third revolutions per minute all the time. So a lot of CDs don't actually work like that.
Really? You would think that they would
do the same thing, right?
Yeah.
But it's interesting. So they have what's called a constant linear velocity, which means that the playing head or the laser, which is replacing your needle, to go from vinyl to CD, that's traveling always at the same speed relative to the disc. And so that means that does that make sense?
Well, let me ask you this: if this was in your research, because I don't know, is it that? Am I to assume that the reader on the CD player is similar to the needle in that it like starts on the outside and kind of goes around in circles, or does it like just go like in and out and in and out kind of? Or
No, it goes around in a spiral. So it slowly, obviously the laser doesn't actually move in that spiral. The disc moves on top of it.
Right.
And the laser just slowly tracks from the outside to the inside.
Right. Okay.
Following that spiral. Yeah.
Okay. Yeah. So it's directly in between what I was saying. It is. Yeah. Okay.
It is moving in and out, but it's not moving around.
Right. Yes. I don't know why. Of course not. Yeah. Okay.
That's right. I mean, who uses CDs now anyway? So we don't really have a good picture of how they work anymore.
For any high school students that are listening, CDs were these shiny objects that if you scratched, they were broken and you got in trouble.
That's right. That's right. Although not like you had to kind of scratch them. You had to sort of do your due diligence to try and scratch them so that they were broken.
Had to mean it.
You had to mean it. That's right. Because it's digital rather than analog. So this is the other big difference between vinyl and CD. Vinyl, when you record it, apparently, you just do one take. That's it. Whatever is in the recording studio, that goes immediately onto the master, which gets transferred to the vinyl. So there's no processing or anything that happens.
Right.
It makes sense, right?
Yeah.
So it's an analog medium. CD needs some processing of information to go from the recording that you make to ones and zeros to binary.
Right.
And those ones and zeros get imprinted into the CD. And so some people argue that the reason that vinyl sounds better, or one of the reasons that it sounds more authentic, is that you don't have any sort of artifacts from going from the original sound to digital.
Right.
It's just analog the whole way. You're getting exactly what they produced in the recording studio.
Right.
Yeah. So, and I don't really know how the digitization process works. So that's maybe something that...
maybe, do I know something that I can share? So
yeah. Oh, do you know? Fantastic.
So that my 1 year of training to be an audio engineer finally has paid off. No, I mean, essentially when you're recording sound, to my knowledge... So when we record sounds, all we're really doing is taking a sample of the sound's amplitude. And how discrete we can get with that is determined by something called the bit depth, which we won't get into right now. But how many times a second you're measuring this amplitude is what we call the sampling rate. And that'll determine which frequencies you're able to accurately capture and reproduce. For digital recording, for CDs, the sample rate is 44.1 kilohertz. And so you might ask, okay, well, where does that number come from? And it's based on a few things, I think. So the first is that humans can hear between 20 hertz, which is like the low bass, and we can hear all the way up to 20 kilohertz, like really shrill sounds. So what does that have to do with 44.1 kilohertz? And so if we think about the characteristics of a wave, and specifically a sound wave, right? The air is wiggling and going back and forth so many times. And meaning, if we want to represent that mathematically, we need the peaks and the troughs. And so in DSP, or digital signal processing, we call this a bipolar signal because it goes from -1 to 1 and then back to -1, and it passes through 0 and all that. So to accurately represent a sound, you'll actually need a sampling rate that's twice the amount of the highest frequency, if that makes sense. And so in that case, if we make recording 44.1 kilohertz, we'll easily capture the whole range of human hearing, because half of that, right? Because again, we need amplitude, trough, right? So half of that would be 2250 hertz, or I should say 22,050 hertz, which easily encompasses all of the range of human hearing. And this number, it actually has a special name. We call it the Nyquist limit, or the Nyquist frequency. And it's always going to be half of your sampling rate for this very reason. So like I'm recording right now at 48 kilohertz. So my Nyquist frequency, or Nyquist limit, is going to be 24 kilohertz. And beyond that, the only other limiting factor, or why they chose this number 44.1 for CDs, is the amount of data you're going to be able to fit on a CD now is going to be about, I think, somewhere between like 60 and 80 minutes worth of music, which for the vast majority of albums is going to be plenty. right? So yeah, it was kind of just like this perfect number for the technology at the time. And you can of course
Right.
record more than that, but it only becomes helpful in like limited circumstances. So
Sure. Okay.
and I get when vinyl people get like that and they kind of, you know, they get very, you know, push up their glasses about it and do the whole bit, right? But you can't tell the difference really beyond that. I mean, there are
bet,
other
yeah.
qualities too, right? Vinyl, you know, I assume
Yeah.
the needle cutting into the groove is a destructive process that has some kind of audio, you know, you hear that's in some way. Maybe that's what they mean by like the warmth of vinyl and it comes out, I don't know, but I forgot how we got here, but I knew something for once.
Yeah, no, that's really interesting. So the Nyquist limit is something that I've heard about from my undergrad, but I'm pretty sure, doesn't it have something to do with aliasing?
Yeah, so aliasing. So, you know, I said, you know, 44.1 kilohertz is the sampling rate, which means half of that, our Nyquist limit frequency is going to be 22,050 hertz.
Yep.
And you'll notice that, you know, if the range of human hearing is from 20 to 20 kilohertz, we have like 2,050 hertz spare room up at the top.
Yeah.
And I think they, you know, another reason why they chose that is you can use that last bit of high end to kind of filter things out and make sure nothing is going above that. Because if you didn't have that kind of filter there and you tried to record a frequency above this Nyquist limit or frequency, what would happen is you'd begin to hear it as a lower frequency, which is kind of wild. And I'll use a classic analogy, or at least as I understand it and learned it, to explain why that will happen. You know, if you're driving down the highway, or for you, the motorway, and you're looking at the car next to you, and you're looking at the tires, you can kind of trick your brain sometimes, or you'll just see it this way as it looks like the tire is spinning backwards, and you know, of course, it's not.
Yeah.
And another example where you might see this is, you know, videos of helicopters. You might see the propellers, the blades, right? They look like they're just in this orthogonal cross pattern, and they're not spinning, but they have to be, right? Otherwise, the helicopter wouldn't be in the air. So what's going on? Well, remember when we were saying you need to capture the peak and the trough of a wave to accurately represent it and reproduce it. And you only have your sampling rate to do that. And so if you have something above the sampling rate, it's going to be on its way, you know, back to a peak or back to a trough in between when you're trying to sample it. And so when you try and reproduce that or play that back and you're interpolating, you know, you're going from one sample to another. Well, if something was already on its way back up or back down, but you're reading it as going from the opposite direction, that interpolation is going to, you know, as far as the computer knows, it's just going from, you know, one step to another step. And it doesn't realize that an entire cycle, or, you know, potentially many more cycles, has happened in between that last, you know, when it took its last sample. And so you'll hear that as a lower pitch. Or in the case of the tire, right, you'll start to see it spin backwards, or you'll see the propeller blades. It looks like they're not moving because the blades are in some kind of multiple of the, you know, your camera's FPS. But pretty wild stuff. Pretty cool.
Cool. All right. Maybe just to finish off that section on, you know, rotations and the various speed and things like that. The needle is tracing around a circle, right? Mm-hmm. Circle has a circumference of 2 pi times the radius. It's doing that at some frequency, so some number of times per second or per minute.
Right.
And so the speed that it's traveling is the total circumference times the frequency, the number of times it traverses that circumference per minute. So it's if you want to write down the formula or think about the formula, it's V.
Give it to me.
Okay, great. The speed is equal to 2 pi times the radius times the frequency. So what you can see from that, as you double the radius, but you keep the frequency the same, you double the speed. Or if you divide the radius by six, as we did with the record, then the speed goes down by a sixth as well.
Yeah. Okay.
And so that means that you need, if you want the same amount of information in the same amount of time, you need that information to be squished by a sixth as well.
Yeah. Okay. Yeah.
So by squished, I mean squished in space.
Right.
You know,
Right.
the density, or another way of thinking about it, if you just have a sine wave etched into that vinyl, then the wavelength will be shrunk by a sixth as well, as you go from the outside to the inside.
Yeah.
Assuming that, what did I say? I think I said it was the radius at the inner radius of vinyl is an inch. That may not actually be right. I don't know.
I mean, it sounds right.
Maybe you can.
I'll bring.
Sounds a bit small to me, but you know, it's easier to talk about than like, I don't know, 1.75 or something.
Right. Yeah, I want to get back to what you were saying about the CDs and their constant linear velocity.
Yeah.
So that's different.
So,
how is that? How is it? How does that work?
Well, so from that formula that you wrote down, if you wanted a constant speed, say we have a 12-inch disc, then if you divide the radius by 6, then you also need to multiply the frequency by 6.
Okay.
Right? And then that would give you the same speed. Or if you halve the radius, then you double the frequency. V is equal to 2 pi RF. The RF doesn't change if you divide one by a number and multiply the other by the same number.
So are you saying that, so what is it then that is changing its frequency? Is it the CD is spinning faster?
That's right,
Okay.
yeah. Just to be clear, I don't think this is the case for all types of CD or disc, but I think like audio CD and CD-ROM and a lot of others use this constant linear frequency. I think it's only up when you get up to certain speeds that it doesn't become practical to change the angular velocity all the time,
right,
as the laser tracks along the disc. So, but this is the case for I think most stock standard things.
Yeah.
So yeah, as the laser tracks from the outside to the inside, the mechanism will spin the disc faster and faster so that it goes up to. So I wrote down some numbers. The slowest speed that the laser tracks over the disc is about 1.2 meters per second, so it's very fast. And that's constant, so that it doesn't matter where the laser is on the disc. It just depends on the disc mechanism and the reader.
Right.
And so if the needle is traveling or the laser is traveling at 1.2 meters per second relative to the disc, that means it's the frequency of the disc, the angular velocity, changes from about 200 to 500 revolutions per minute, which is, if you divide that by 60, like 3 to something. Let's do it properly. So yeah, it's 8 1/3 is the largest number of revolutions per second. So it's pretty quick.
Yeah, for something very, very tiny.
Yeah, and that's the slowest. So you can get faster than that as well. It depends on the disc that you have.
So to put a bow on this, to see if I got this, fingers crossed. With vinyl, it's the change factor is in the tangential velocity, but what's different about CD is that it's the angular velocity. That's the change factor. Change factor sounds so metal. I don't know why I said it. It's just the cause of the change. All right. I didn't know that. That's cool as hell. Today I learned.
Yeah, it is interesting. Hey. Yeah. And so the upshot of that is it means that the bit density, so like we were talking about the density of sound in vinyls. Well, you have a density of bits in CDs because it's digital. And those bits have a constant density throughout the whole disc. So you don't have any problems when you get to you get close to the center of the disc because like you had with vinyl, because the density is the same. So you have a constant bit rate throughout the whole thing, number of bits per second, and the size of those bits, physically, the size is the same. So if you wanted a constant bit rate and a constant angular frequency, then you would need to reduce the size of those bits, and eventually you'd have a problem.
Right.
So maybe we can talk about the mechanism behind the vinyls and CDs.
Yeah, you say physical size of bits, and that piques my interest.
The way that bits are stored on a CD also depends a little bit on the type of CD you have. But basically, you've got a laser which is shining on like an aluminium surface or something that's shiny, right? And if depending on the state of the disc at that point, you can either have the light reflected off the surface, or it can be kind of scattered. And basically there's a reader that picks up the reflected laser light, and it can either read as sort of high amplitude, it can be reflected, or it reads low amplitude, so light or dark, basically. Mm. So the laser is shining on the disc, and it can either hit something shiny or it can hit something dull. And there's a reader which picks up whether or not the laser reflects from the disc. So basically, if it hits something shiny, the reader picks it up as having reflected, and it's a light reading, or it could be a dark reading if it hits something dull. And so if you have a writable disc, then the dull part is where it has been, where the disc has been burnt by a writing laser. And so when you have some coating over the disc, and when you're writing onto the disc, you're imprinting little dark spots, right? And so those dark spots, you won't have, the laser will be scattered off it, and the reader won't pick up anything. So the way the actual encoding works is that you might think, okay, well, you just encode a light spot as a 1 and a dark spot as a 0. The way I think they actually do it, though, is that any change from light to dark is read as a 1. Okay. And whenever it's the same, so you have some constant duration of time, and if between two of those durations there's no change, so it's still dark or it's still light, that's a 0, and if there is a change, it's a 1. So if you have a long string of zeros, that could just be a long pit of darkness or a long stretch of light.
Too real, man, too real. Never thought I would be empathizing with the CD, but here I am.
But so that was a writable disc. You can also have just the sort of standard audio disc or manufactured disc, which instead of using little dark spots and light spots, which can sort of fade over time, you have literal imprinting of information. So you have pits which are dug into the shiny surface, and that's what they're called, pits. So they're little holes, and lands. That's the other version, or the other bit type. And a land is just a flat, the flat surface around a pit. Mm-hmm. So the reason that the light shining onto a pit is dark. Actually, firstly, before I should say that, so it's a bit confusing, but they imprint it on the top side, but the laser reads it from the bottom side. So a pit, even though it's called a pit, is actually a bump. Yeah. Yeah, it's flipped over. And so when the laser hits a bump, otherwise known as a pit, half of the spot is shining off the bump, and the rest of the spot is shining off the flat surface around the bump. So the bump is sort of smaller than the spot of light. Okay. A little bit. And the size of that bump is a quarter of a wavelength of the light that is used. Now, if you draw a little diagram, I'll see if I can, I don't know, maybe the listener wants to follow along at home or something like that.
He's got the pen, ladies and gentlemen. He's got the pen.
Got the pen back. Basically, what is being produced is destructive interference. So if you have two waves and one, so if you just draw a little sine wave and then you draw another one, which is completely out of phase. So the peaks of one wave correspond to the troughs of another wave. So if you add those two waves together, peak for trough and trough for peak, you'll get 0 everywhere. They'll cancel each other out. And so if you draw a little ledge and have some light reflecting off the top of the ledge and some light reflecting off the bottom of the ledge, well, if that ledge height is a quarter wavelength, then after the light reflecting off the bottom gets all the way back and catches up with the light reflecting off the top, it will be 2 times a quarter wavelength or a half wavelength out of phase with the original.
Right, okay.
And so half wavelength out of phase means peaks line up with troughs.
And that corresponds to your 0 bit?
Yeah, so the light destructively interferes with itself. I've drawn a very horrible diagram there. Anyway, but hopefully you get the idea. So when the light hits a bump or a pit, some of the light reflects off the top of the bump, some of it reflects off the flat surface around the bump, and that light destructively interferes with itself. So the reader picks that up as a dark spot. And again, you have that whenever you change from light to dark or dark to light, that's a 1, and then no change is a 0.
I appreciate the levels of using light waves to ultimately produce sound waves. Something very...
It's pretty cool, huh?
Yeah. Something very poetic about it that I like.
And so you can imagine then that the size of this spot of light is kind of going to be limiting in some sense the amount of information that you can squish onto this disk.
Right.
Because the lateral distance between bumps, right, has to be larger than the size of that spot. Because you can't have a spot that is hitting a bump and also a little bit of a bump or lands on a different track. But that's why Blu-ray is more advanced than the original laser discs or CD-ROMs. It's using a smaller wavelength of light, which means that the spot of light is smaller, so you can pack more information into that.
Yeah, okay.
That disc.
Interesting.
Yeah. So anyway, that was a lot of information.
Cool as hell. No, that's cool as hell. I listen. My initial understanding of CDs was much simpler than that, but that's cool as hell. That's really cool.
What about your understanding? So how do you understand vinyls to work?
All right. So you have, I mean, this is going to get tricky quick. You have your record, which is made out of some kind of wax. Although it you know, let's just call it wax for right now.
Yeah, I think it's a plastic of some kind.
Yeah. And then you have your needle, and on your plastic, on your wax, you have your grooves, and the needle goes on the grooves. And I guess there's those two things, right, that I guess I would assume you need, which is you need volume, right, or you know, amplitude, and you need frequency. And so I would imagine that the motions that a needle can go in correspond to that somehow. Maybe let me use all of the knowledge that I have to make an informed guess here. I'm going to say that up and down corresponds to amplitude, if I'm even right about this, and left and right has something to do with frequency.
You're pretty close. Cool. Yeah, not bad at all. This is certainly not something I knew before having a little squiz online. And there's actually a really good animation.
Hold on. What online?
Squiz?
That is some Australianism. You need to...
It's a bit of a slang term. Sorry about that. Just means a look, I guess.
Okay, there we go.
Squiz. It's good. It's a good word, I think.
It jumped out at me. Squiz.
So there's a good animation that I think we can hopefully put in the description of the podcast so that you can find it.
This is basically this I'm Girl link, Imgur.
Yes, that's right. Yeah.
Oh, let me pull this up. Okay. Oh, look at this. This is a great animation, listeners.
Yeah, it is good, huh? So you're right that there are two types of motion that the needle can have. Basically, it can go... The depth of the groove can increase or decrease, so the needle can move up and down, or the groove itself can move side to side. So up and down, left to right.
Right.
But it doesn't exactly correspond to amplitude and frequency because the size of variation in those motions correspond to the amplitude, while the frequency of those motions correspond to the frequency. But... Okay.
Yeah. All right. Yeah, that makes sense.
Yeah. There are still two types of motion. We can have two tracks stored into the one groove. And those two tracks correspond to the left channel and the right channel.
I was going to say that's awfully convenient for stereo recordings.
Yeah, exactly. But it's a bit tricky because it's not exactly the fact that, for example, up and down corresponds to left channel, side to side corresponds to right channel.
Right.
And the reason it's not that is because the side to side has a greater... you can modulate the side to side motion much more. It can have a greater amplitude than you can the up and down. So instead, you kind of turn that whole system 45 degrees. So if you have a sheet of paper or a book or something like that as a prop, you can imagine if you hold the book vertically, then one side corresponds to up and down motion, the other side corresponds to left and right. Instead, what they do is they tilt the book 45 degrees.
Okay.
And now, if you're imagine that the point along the edge of the book corresponds to where the where the base of the ridge is. So the deepest point of that ridge. One motion corresponds to the motion along one side of the book. So the deepest point of the ridge is moving diagonally up and to the right, or it's moving diagonally up and to the left.
Right.
And so in this way, you can have like a full sort of amplitude between the left and right channels. You can have you have the same amount of space available for storing information and storing sound.
Right.
So does that make sense?
I think so. I mean, my initial thought is that there would be some physical limit to how much amplitude information you could store, because at some point, you could have a groove that's 100 miles wide, but if your needle's only, a needle, it's not going to be able to cover that.
Yeah, so as you go deeper, your groove gets wider and the needle goes further down inside it. So yeah, you could get wider and wider grooves. But obviously with this book analogy here, as the amplitude increases, you're also going further and further to the left and right.
Right. Okay.
So you have sort of lateral movement as well as vertical.
Right.
And that's what I meant when I said you need more space to get louder.
Okay. Yeah. Yeah.
So you need literally the space between grooves needs to be larger so that the needle can move further and further side to side.
Yeah. The space between grooves. Yes. You're ready to lead a funk band, man. Gotta have that space between the grooves.
We've got a couple of good band names tonight. Yeah.
Yeah.
Yeah. So in fact, this, according to some audio engineer that I listened to an interview with, if you have a really long record or a long album, it sounds quieter. Whereas if you have a shorter album, you get much more dynamic range when you're recording onto vinyl, which is quite cool.
Yeah, yeah. And I get, and just so, and then in the other direction, it's just the needle becomes a vibrating thing, and then you just take that vibration and you amplify it. I mean,
it
sounds obvious now that I say it. We need amplifiers.
Well, yeah, but it does get converted into an electrical signal first. So basically, you're right. So the needle is vibrating because it's tracking one of these grooves, and there are two different directions in which it can vibrate. And there are two coils within the cartridge. Yeah, not a very interesting name, but anyway, so the needle is on this little lever, which is the other end of the lever is housed inside the cartridge, which is all inside this little playing head. And so on the other side of the lever is a little magnet, and so the magnet is vibrating when the needle vibrates. And there are two coils of wire that are oriented 90 degrees probably from one another. And so one type of motion of the magnet causes a change in magnetic flux through one of these coils.
Right.
And then the other type of motion causes a change in magnetic flux through the other type of coil.
Yeah.
And one of these very fundamental, amazing, special rules of electromagnetism is that if you have a changing magnetic field in the presence of a wire or something like that, it creates an EMF, an electromotive force. So it causes charges to move inside that coil of wire. What that means is that it transforms the oscillation of this needle, or equivalently the oscillation of the magnet, into an electrical signal. And then that electrical signal gets amplified.
And then you see the process in reverse, essentially. That's
exactly right, yeah.
My audio engineering, that 1 year paid off finally.
Yeah, I bet. No, that's right. Yeah, so the way a speaker works is exactly the opposite. You've got a magnet which is attached to a diaphragm, the thing that moves to produce the sound, and that magnet is sitting inside a copper coil. And so whenever the electrical current inside that coil changes, it produces a force on the magnet which causes it to vibrate. And so hence you get sound.
We move the air, and then it goes to the magnets in our head, which do the same thing.
Only if you've had the vaccine, right?
Yeah. Okay. Yeah. This is. So in fact, I'm literally speechless right now. I'm like, this thing that has been a part of my life. I finally know.
So if we were in 4 dimensions rather than 3, you could have like 3 stereo tracks, right? Because you could have 3 degrees of freedom, which are all perpendicular to the groove. Whereas in 3 dimensions, you can only have 2 degrees of freedom that are perpendicular to the groove.
3 dimensions to the groove. You are starting a funk band. I know it. You just haven't told me yet. Oh my God. Yeah.
I think all our episodes are sort of melding into each other. How do records work with string theory now? We've got to talk about that.
Yeah. Oh, this is so cool. Well, thank you for answering my questions. I'm glad I was able to contribute a little bit.
We both were answering this question together.
Yes. As always, if anybody has a follow-up question or has a comment, question, concern, of course, let us know in the email, which is listed in the description, because we totally have that prepared as of the recording of this show. And we would love to hear from everybody. If you have any suggestions for topics, questions, that's kind of what I just said. Campbell, any final thoughts, any final words?
If anyone steals the band names that we've come up with within this episode, we will hunt you down. We will find you and sue you.
Don't forget to buy your tickets to see The Pen when we are live at Madison Square Garden. And just as always, thank you for listening to Question Field. We will see you. Well, you will hear us next time, ladies and gentlemen. And thanks for listening.
You've been listening to Question Field. Question Field is a Gain Media production and is produced by its hosts Campbell McLaughlin and Brian Buchanan. For more information, please check us out on Instagram at QuestionFieldPod, on Twitter at QuestFieldPod, and on TikTok at QuestionField. If you have a question you'd like to submit, or would simply like to leave a message, please send us an email at questionfieldpod@gmail.com. Recently, the James Webb Telescope discovered 5 new stars located in the review section of your favorite podcast app. Thank you for listening.